Good day everyone, welcome to Bright Engineering. Today we are going to look at voltage distribution over suspension insulator string. Alright, so we are going to look at this question. When a line of 3-phase 11 kV system is suspended by a string of 3 identical insulators, the self-capacitance of each disc is found to be 70 times the shunt capacitance to ground. So we are to find the voltage distribution across each insulator and then the string efficiency, right? So for better understanding, let's look at a diagram or a schematic to understand this better. All right, so this is how it looks like. So we have this string here, and this string are made of 3 identical insulators, right? So we know that this string itself is attached to this tower. So this is our tower line with a voltage across this particular string as V, right? And we know that it's attached to it by this arm, and then this is the line that this particular string is connected to. So the line is being transmitted with the help of this particular string, right? But then with this being said, let's look at how it's going to aid us in our calculations. We know that this is an insulator, this is an insulator, but then in between these insulators we have a conducting material, that's a metal. We have a metal here, metal here, metal here, right? And these are conductors of electricity. So it means that if you are to take away this particular insulator, the only thing that is left here is air between it, right? And if there is air between it, it means that it's behaving more or less like a capacitor, right? Because we know that when voltage is applied across a capacitor, it's applied across 2 plates with spaces in between, right? So we can just redraw this in this form to get this. So still we know that this is our support, this is our line, right? And now we have these capacitors, and we are saying that these are identical insulators. So let's say the capacitance of these capacitors will be represented by C, right? But then interestingly, this is a tower and this is a metal, and in between these capacitors two are metals, right? So it means that between these metals two there is air. It means this also acts like a capacitor. So we can also represent in between these metals with capacitors. Please, I hope you understand that. Yeah. So we can present this with capacitors, this with capacitors, like this, right? Good. So with this being said, we know that this is the total voltage across the string, which is our V, and then we are to find the voltage that is across this insulators each, right? So we are going to make the voltage across this be our V1, across the second one be our V2, and across this be our V3, right? And of course, we are going to have a different capacitor here too. So we are going to make this also C1, and then C1 because they are also identical, right? So now we have to find for the calculations, or we have to assign to them directions of the current. If this is our line and our line is producing current this way, it means that current is going to flow this way, and of course this way. And because this is V3, let's assign it with I3 so that we don't confuse ourselves. So capital I3 here and a small I3 here. When it gets here, it would split. You get current here and the current here. So capital I2 here and a small I2 here. The same thing applies to this side. It's an I1 here and an I1 here, right? So now we are going to write the formulas for these things in and out of itself, right? But before we continue, let's look at this capacitor and then this capacitor. This capacitor is what we called the self or mutual capacitance, because it is something that is found inside the insulator, right? And this is the shunt capacitance because it exists between these two metals. Please, am I getting it? Are we getting it? Sorry. So now we have something we call K. And then we are saying that K is just the ratio of this shunt capacitance to this mutual or self capacitance. So our K is equal to C1 over C, right? So it means that wherever we see C1, we can say our C1 is equal to CK or KC, anyhow you want to write it. So it means that we can, instead of C1, 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 we can represent all these with CK, 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 right? Good. So now let's look at the current directions. To make our calculations more simpler and easier, let's start from V1. So if you want to find the current that is flowing through V1 from Ohm's law, we know that I is equal to V over R, right? But in this time around, we are dealing with capacitances and not resistance, right? So we know that instead of R, we are going to deal with XC, right? And XC here is going to give us 1 over omega C, right? So now current 1, which is I1, is going to be V1 over 1 over omega C, right? And this is the same as omega C V1. So we are done with the first current. Now I2. When we are calculating for I2, right, we know that I2 is just the addition of these two currents, because the amount of current entering a node is the same as the amount of current that leaves that particular node, right? So I2 is capital I1 plus small I1, right? And capital I1 is just V1 WC as we found. So yes, we have I2, and we know that I2 is the current flowing through this particular capacitor. So it's just V2 divided by this capacitance, which is 1 over omega C, right? So I2 is going to give us V2 omega C, and then I1 is also going to give us V1 omega C, right? Plus small I1, and small I1 is going to be the voltage at this particular node divided by the capacitance here, which is also going to give us V1 omega C1 based on our capacitor. But then interestingly here, we've already found out that we can represent this C1 with KC or CK, right? So our V2 omega C is going to be V1 omega C plus V1 omega CK. So when we look at all these things, what is common to them is omega C. So straight away, we can just cancel omega C out, and then we are going to get V2 is equal to V1 plus V1K, right? So V1 is also common to this part. So we have V2 is equal to V1 out. Now we are getting 1 plus K for V2, right? So now let's find for I32 as well. So now I3 is also equal to this I2 and then this small I2, because when it hits this node, it would split up, right? So we are getting I3 to be I2 plus I2. And I3, of course, is going to be our V3 times the capacitor, which is omega C. And I2 is V2 times the capacitor, which is also omega C, plus our I2, right? But then let's look at something here. At this particular node, the voltage that was left here was V1. But at this particular node, the voltage that is left here is not just V2, but it is the addition of these two. Note, this is the conductor. And when the conductor is coming this way, of course, this particular capacitance is going to drop it. So we are going to get a voltage drop. But then the voltage that is left here at this particular node is going to be the addition of these two, right? So when it drops here, then now we are left with V1. So here, the voltage across this node is going to be V1 plus V2, right? So our I2 instead is going to be V1 plus V2 times omega C1. And now we can represent omega C12 by CK. So we are getting V3 omega C is equal to V2 omega C plus V1 plus V2 omega CK, right? We know that omega C is common to all of them, so we can cancel that out and get V3 is equal to V2 plus V1 plus V2 and then multiplying by K, right? So when we expand, we'll get V3 is equal to V2 plus V1K plus V2K. Now we have V2 here, we have V2 here, so we can group like terms. So we are getting V3 is equal to V2 into brackets 1 plus K plus V1K, right? And this is our expression for V3. But then we already found for V2 that V2 is V1 1 plus K. So we can just substitute that into this equation, and then we are getting V3 is equal to V2, which is V1 1 plus k multiplied by 1 plus k and then plus v1 k, right? So now we can expand this, and we are getting v3 is equals to v1. This is going to give us k squared plus 2k plus 1 plus v1 k. Please, I hope we understand this. Yes. And then here, because v1 is common to these, we can just extract v1 out and then add this k to this to get v3 is equal to v1 bracket k squared plus 3k plus 1. So now we have our v2 here and then we have our v3 here, right? And then when we started, we said that the voltage that is across this particular string is equal to these three voltages, right? Because it's this particular voltage that will be dropping from here and then here for us to get even v1 here, right? So it means when we add up all these voltages, we have to get this ideal or this particular voltage, right? So now we can say that our v is equal to v1 plus v2 plus v3, right? I hope this is understandable, right? So now we already know v2 and we know v3, so we just have to put it in there. So our v is going to be v1 plus v2 is v1 into brackets 1 plus k, and our v3 is also v1 into brackets k squared plus 3k plus 1, and this is for our total voltage, right? So in order to find this, the question said that each line of a three-phase 11 kV system, so it means the voltage that have been given to us is three-phase voltage, and because we are talking about a single insulator, right, or a single string, it means that we have to convert this three-phase voltage into a single phase voltage, right? So we are just going to do that. So v phase is going to be 11k, which is 11 times 10 raised to the power 3 divided by root 3, right? And then we are going to get 6.35 kV for the single phase. So here we can also find for our k, because we said that our k is just the C1 over C, right? And then the question said that we have the self-capacitance of each disc to be found to be 70 times the shunt capacitance, right? So now our k is this 1 over 70, which is going to give us 0.014, right? So we have these two values and then we can just insert it in this. So now we have 6.35 times 10 raised to the power 3 equals to v1 plus v1 into brackets 1 plus 0.014 plus v1 into brackets 0.014 squared plus 3 0.014 plus 1, right? Good. Have v1 here plus this is going to give us 1.014 v1. This is going to give us plus 1.042 v1, right? So when you add this up, you're getting 6.35 times 10 raised to the power 3 is equal to 3.056 v1. So when we divide this by 3.5 divide 3.056, now we are getting our v1 to be equal to 2.077 kilovolts, right? So now that we have our v1, we can straight away find our v2, because our v2 is just this v1 into brackets 1 plus k, right, which is this, because we represented this by v2, so it's just 1.04 times v1, right? So now our v2 is going to give 1.014 times v1, which is 2.077 kilovolts, and now our v2 is going to give us 2.106 kilovolts. And now our v32 is the same as 1.042 v1 per the calculations that we made earlier, right? So v3 is going to be 1.042 times v1, which is the 2.077 kilovolts, and now v3 is also going to give us 2.164 kilovolts, right? So now we know our V1 to be 2.077 kilovolts, our V2 to be 2.106 kilovolts, and our V3 to be 2.164 kilovolts, right? So this solves the first question, which is the voltage distribution across each insulator. Mind you, for the voltage distribution across the insulators, we indicated them with V1, V2, and then V3, right? And we said that when we add these up, it should also give us the phase voltage. So you can add up these and then see if you are truly going to get 6.35 kilovolts, right? Good. So now with this being said, let's go to the second question, which is the string efficiency. And in order to find the string efficiency, we say that it is the total voltage, total phase voltage, of course, over the number of discs that we have times the voltage of disc closest to the conductor, right? So now our total voltage that we have is 6.35 kilovolts. The number of discs that we were working with were 3, and then the voltage of the disc that's closest to the conductor is this V3, because I said that the string is carrying the conductor here. So this is our conductor and this is our support, right? So the disc that is closest to it is this particular disc, and the voltage across this disc is this V3, right? So it's going to be times V3, and now we know that our V32 is 2.164 kilovolts, right? And this is going to give us 0.978, and of course its efficiency we are finding, so times 100%, and now we are going to get 97.8%, right? So the efficiency that you get is most at times dependent on the ratio of the shunt capacitance to the self capacitance. As it reduces, it means that the efficiency was also reduced. As it increases, the efficiency was also increasing. Please don't forget to subscribe to the page, like and share. Thank you very much.